Hello, am I audible? Hello. Okay. Okay. So we will wait for 2-3 minutes, then we will start. Hmm. Hello. Hello. Less. Okay. Mm, Actually, the recordings of the video will be available in the portal, NPTEL Gate portal, after a few days. I don't know, but it will be available after some time. Okay. Okay. I think the whiteboard is visual, right? Okay, so let's start. Today we will discuss statistical mechanics. Last day we have seen that from the laws of thermodynamics we can write TdS equal to du plus Pdv for a gaseous system, right? Now I am writing this internal energy by E. There may be other terms also in this expression, as you know, there may be one more term like mu dn. Now what is mu? Mu is the chemical potential and n is the number of particles. Okay. So here you see that E is a function of S, V and N. Okay. From this you can also write ds equal to dE by T plus Pdv by T minus mu dn by T. Okay. So here S equal to, I mean S is a function of T, sorry, not T. S is a function of E, V and N. E, V and N. Yes. Okay. So the change of S is written in terms of the change of E, change of V and change of N. I mean dE, dV and dN. So S is a function of E, V and N. And here you can see that this 1 by T is actually the first order derivative of S with respect to E with V and N constant. Okay. So this T is function of this 1 by T is a function of E, V and N. Okay. But S cannot be expressed as a function of T and other things, right? Okay. So as you can see here, this 1 over T is given by del S del E at constant V and constant N. Okay. Similarly, you can see here P by T is equal to del S del V at constant E and constant N. Okay. So we get three equations from the expression I have written in the previous slide. Okay, now I will define entropy S in terms of number of microstates in the system. Okay, so S can be written as kb ln omega. Now what is kb? Kb is Boltzmann constant. This is a constant. Okay, nothing significant here. Now what is omega? Omega is the number of microstates corresponding to a macrostate. Okay, this omega is a function of E, V and N. So S is a function of E, V and N. Now let's consider an isolated system. It means energy of the system is constant, volume of the system is constant, and number of particles is also constant. So there are three conserved quantities in an isolated system. These are energy, volume and number of particles. I have told in the previous class that entropy, the change of entropy is zero in equilibrium. Okay, it means entropy is maximized. So in equilibrium for an isolated system we have ds equal to 0, the change of entropy 0, or entropy is maximized. It means this omega is also maximized. So for an isolated system at equilibrium we have maximum values of this omega. This omega is the number of microstates. Now let's consider two subsystems of an isolated system. Okay, so this is an isolated system. It has two subsystems. This is subsystem 1, this is subsystem 2. There may be exchange of energy between subsystem 1 and subsystem 2. There may be also exchange of particles between subsystem 1 and subsystem 2. But this total system, I mean overall this system is isolated from the rest of the universe or the environment. Okay, so as the total system is isolated, we have the total energy E1 plus E2 equal to E total. This E total is constant, where E1 is the energy for this subsystem 1 and E2 is the energy for this subsystem 2. Et is the total energy. As the overall system is isolated, we have Et equal to constant. Similarly, we have V1 plus V2 equal to Vt, which is constant, and N1 plus N2 equal to Nt, which is also constant. As the overall system is isolated, we have Et equal to constant, Vt equal to constant, and Nt equal to constant. Now, what is the number of microstates of the overall system? This omega t is the number of microstates of the overall system. This can be written as omega 1 times omega 2, where omega 1 is the number of microstates for the subsystem 1 and omega 2 is the number of microstates of the subsystem 2. Now take logarithm on both sides. I have told before that log of omega is equal to S by Kb. So here Kb, the Boltzmann constant, is a constant. So the total entropy of the system is equal to S1 plus S2. The entropy of the first subsystem and the entropy of the second subsystem. Sum of these two things. Okay. This is the total entropy of the system. But at equilibrium, I have told that this ds equal to 0. Now what is ds? This is this. So we have ds1 equal to minus ds2. Now E1 plus E2 is also constant, as the overall system is an isolated system. Yes. Okay. Previous slide. This slide, right? Okay. 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 Fine. Okay. So now I will take differentiation on both sides of this equation. As you know, the differentiation of constant is 0. So in the right hand side we have 0, and in the left hand side we have dE1 plus dE2. So we have dE1 equal to minus dE2. So from these two equations, ds1 equal to minus ds2 and dE1 equal to minus dE2, we can write it like this. So del s1 del s1 del e1 equal to del s2 del e2. Now what is this? Can anyone tell me what is this quantity? Right, this is 1 by t. Now let's say this is the temperature of the first subsystem. So I denote it like 1 by T1. Okay. Similarly, this is the temperature of the second subsystem. So we have T1 equal to T2. So this is the condition of thermal equilibrium of two subsystems. So the temperatures of the two subsystems are equal in thermal equilibrium. We all know this. Similarly, using this V1 plus V2 equal to constant, you can show that P1 equal to P2 at equilibrium, which means pressure of the two subsystems are equal at equilibrium. Now this equilibrium is called mechanical equilibrium. We also have total number of particles constant, n1 plus n2 equal to constant. From this you can show that mu1 equal to mu2. This is called chemical equilibrium, condition for chemical equilibrium. At chemical equilibrium we have equal chemical potential of the two subsystems. Okay. Tell me, what was your question? Hello. Right. uh, you were present in the last class, right? Okay, I was explaining that at the end. Okay, suppose you know that temperature is the driving force of heat energy, right? You know that heat flows from high temperature to low temperature. Similarly, you have uh, chemical potential as the driving force of particle. Okay, if chemical potential, let's say chemical potential of the subsystem 1 is greater than the chemical potential of the subsystem 2, then what will happen? Particles will flow from subsystem 1 to subsystem 2. Okay, similarly, if mu2 is greater than mu1, then particles will flow from subsystem 2 to subsystem 1. And at equilibrium we have mu1 equal to mu2, so there is no flow of particles between the net flow of particles between these two subsystems, right? Clear, I think. Okay, fine. Uh, that's same, almost same. Like this gives right gives free energy can also be written like this. I was writing it by small g last time, last class, right? Okay. Hmm. Pressure equal means there is no right, right. Pressure of the two subsystems is equal at mechanical equilibrium, so there is no uh, net change of volume, right, of the two subsystems. Okay, right, right, that's also correct. right? That's actually the definition of mechanical equilibrium in terms of classical mechanics, right? You have F equal to 0 at equilibrium. That's called mechanical equilibrium. And so this force can be written in terms of, this is not volume, right? This is potential. So let's write it something else. U, let's say U. Okay, so gradient of this potential is actually giving you the force. Okay, so this grad U is equal to 0 at mechanical equilibrium, and here this force equal to pressure. I'm not writing it like this, sorry. So the magnitude of the force is equal to pressure times area, right? So the net pressure is 0. I mean here you have P1 plus, I mean P1 equal to P2. Okay, right. So this means net force is 0. Okay, okay. So these are the three types of equilibrium. Okay, so now let's consider again two subsystems. One is S and another is R. Here we will assume that this subsystem S, or which will I will call system onwards. Okay, this is much smaller than this reservoir R. Okay, R is the reservoir. Okay, and the overall system, I mean S plus R, is the total system or the universe, you can say. So S plus R is an isolated system. So the total energy, I mean this ES plus ER equal to ET, this is constant. Now we'll further assume that there is exchange of energy between S and R. So S can vary, ER can also vary, but S plus ER is constant. But in S, the number of particles in system S is constant. So NR is also constant, as we know. NS plus NR is also constant. Similarly, Vs, the volume, constant. So Vr is also constant. So we are considering only the exchange of energy between the system S and the reservoir R. Okay. Now we'll try to find out the probability of finding a particle with some energy Es. Okay, as I have told before, this Es can vary, so there will be a distribution, I mean probability distribution of finding the particle with some particular energy. Okay, so let's try to find out. Okay, here this system S is much smaller than the reservoir R, so we'll assume that S is much smaller than ER. Okay, So the probability of finding the system with a particular energy S will denote it by this PS. Okay, this will be proportional to the number of microstates of the reservoir with the energy ER. Okay, the number of microstates in the reservoir omega R as a function of ER can be written by this. Here Et is the total energy and S is the energy of the subsystem, I mean system. Now I will take log on both sides. Now I will use this approximation. As I have told before, this S is much smaller than ER, so S is also much smaller than ET. Now I will expand it in Taylor series. So in the first term we have this term log of this omega R function of Et minus differentiation of this term with respect to E at E equal to Et times S plus some higher order terms which we will neglect because we have considered this assumption S is much smaller than Et. So in the first term you can see that this Et is the total energy of the system and the universe. So this is constant because we know that system plus universe is an isolated system and the energy of an isolated system is constant. So this first term is constant. Now what is this second term? I will denote this entropy by kb log of omega. So we can write it like this. Now del S del E is given by 1 over T. Now we are considering the entropy of the reservoir here. Here is SR. So it will be 1 over TR. The TR is the temperature of the reservoir. Okay. So log of this omega R is equal to this thing. So omega R this will be proportional to S by kb TR. Here TR is the temperature of the reservoir. From now onwards I will call T equal to TR. Okay, so this is equal to S by kb T. As I have said before, PS, the probability of finding the system with some particular energy S is proportional to this omega R function of ER, and we have just found that this is proportional to S by kBt. Now this 1 over kBt, I will define it like beta. So PS is proportional to beta ES. So the constant A is the constant of proportionality. Okay, and we also know that the probability sum of the probabilities is always 1. Now put it here, you will get A sum over A S e to the power minus beta ES equal to 1. So A equal to 1 by this. So PS equal to this. We can write it also by this thing. PS equal to e to the power minus beta ES by Z. Now what is Z? Right. Z is the canonical partition function. Now what is canonical here? Canonical distribution, I mean the probability distribution I have just written here is called canonical distribution because we have exchange of energy between the system and the reservoir, but there is no exchange of particles between the system and the reservoir. If you have exchange of particles between the system and the reservoir, then it will be called grand canonical partition function or macro canonical partition function. Okay, but this is the canonical partition function. Yes. Is and R. Okay. Here, right? So here I am just telling it very short because we are already running out of time. Okay. So here the system is much smaller than the reservoir. Okay, so we have this approximation. ES is much smaller than ER, and the total I mean system and the reservoir system plus reservoir is an isolated system. Okay, we have assumed that. So the total energy is constant. Okay, so the number of microstates in the reservoir omega r is given by this thing. Now I have just expanded in Taylor series up to first order in ES because we have this condition ES is much smaller than ET. So we are neglecting the higher order terms, and here I have written this in terms of the temperature of the reservoir because you know that this is equal to log of omega is equal to 1 by kb times s, and this del s del e is equal to 1 over t. So I am writing it like this, and so we have this omega r is a function of ER is proportional to minus ES by kBt. Okay, here T is the temperature of the reservoir. So the probability of finding the system with some particular energy ES is proportional to this thing. Okay, this exponential thing. Okay, and here we are just considering that the sum of the all the probabilities is always 1. So from that we are getting this normalization constant A which is equal to 1 over z. Here z is the canonical partition function. Okay, so this is the definition of canonical partition function, and this Helmholtz free energy, which means E minus Ts, which I have told in the previous class, is equal to this thing, minus kBt log of z. If I get some time at the end, then I will show it how to get this relation. Okay, so we had this entropy as function of E, V and T, sorry, E, V and N. Now this Helmholtz free energy will be function of T, V and N. Okay, now let's solve a problem, then we'll discuss later. question from this. Hello, am I audible? No question. Okay. Hello, hello. Are you saying something? Oh, no question. Okay. So let's solve another problem. Okay. Any question or doubt? Hello, am I audible? Okay, no question, right? Okay, fine. uh, let's solve another question. Hello, am I audible? Okay. One by one. Okay. Hello. Okay. For this question, you should know that for Bose-Einstein distribution, you can place any number of particles in one energy level, right? And for Fermi-Dirac distribution, you can place at most one particle in one energy level. Okay. So let's say there are 10 particles. Okay, you can all place them in one energy levels if they are bosonic. I mean, if they follow Bose-Einstein statistics, or you can place them like in one energy level you have 3, in another energy level you have 2, and so on. You can also place one in one energy level, each particle in each energy level. Okay, but for boson for Fermi-Dirac distribution, you can maximum place one particle in one energy level. And the main difference between these particles which follow Bose-Einstein and Fermi-Dirac distribution is that the particles which follow Bose-Einstein distribution is called bosons, and these bosons are integer spin particles. Okay, and the particles which follow Fermi-Dirac distribution, they are called fermions. These are spin half or half integer spin particles. Okay, example of this fermion, there are many, like electron, proton, neutron, etc. And the example of boson, we all know, photon. Okay, phonon, etc. Okay, clear? We'll later discuss about it. Next week we will discuss about thermodynamics, mainly covering the topics of entropy and other things. And uh, I think next of that week we'll discuss about Bose-Einstein distribution and Fermi-Dirac distribution in details. Okay. Okay. Any other question? Hmm? What? Z. Hmm. Okay. Why? Right. Right. Okay. Okay. No, 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 not that. Actually, we are getting. So I am sharing my screen. Okay. So when the screen is visible, right? Okay. So you have this. Why this, right? That's your question, right? Okay. Why there is 1 by n factorial? Here n is 2 in our question, right? There are how many particles? 2 particles, right? In that question. Okay. So why 1 by n factorial? That's your question. This 1 by n factorial is called Gibbs factor. Okay. So I am explaining to you why there is 1 over n factorial. So let's say uh, there are 3 particles. Okay. So if the particles, sorry, are distinguishable, so we should write them in with different notations. Let's say one is like this, the another is this, and the another is this. Okay, so there are 3 particles. So how many ways you can arrange them? I mean, just the order. So let's see how many. They are distinguishable, right? Okay, so let's write it properly. This is one configuration. The other will be this. So there are 6 configurations, okay, for 3 of them. If n equal to 3, you have 6, which is 3 factorial actually. So let's say there are n particles, okay, and you have n positions like this, okay. You have to fill any one of them, okay. So for the first particle, how many ways you can fill them? N, right? You can choose any one of them. Clear? So let's say for the first particle, you can choose it like this, and for the second particle there are how many options? N minus 1 options, right? Because you have filled one already. And for the next you have n minus 2 and so on up to 1. For the last particle you have just one option left, you have to fill it like this, okay. So it will be equal to n factorial, okay, if they are distinguishable. But if the particles are indistinguishable, then the partition function will be less. I mean, it will be number of configurations will be less actually. It will be 1 over n factorial of the number of configurations of this, okay. So we have this 1 over n factorial, okay. Clear? Okay. It's already 9:15, so I think we'll stop here today. Next Saturday we'll discuss thermodynamics and entropy. If we have some extra time next week, then I will show this derivation of f equal to minus kbt log of z, okay. Okay, let's stop here. What's question? Tell me. My name is Soikot. Mail ID. I don't think it's required actually. So if the email ID is required, then it will be on the portal, okay. NPTEL get portal. If it's there, then otherwise I cannot share it. Okay. Okay. So I am leaving. Okay. Let's stop here.